Hello, my name is Stephan Meylan, and my talk today is entitled Quantifying Lexical Ambiguity in Speech to and from English Learning Children. This is joint work with Jess Mankiewicz, who is also a first author, Sammy Floyd, Hugh Rabagliati, and Mahesh Srinivasan. Lexical ambiguity is one of the key features of natural languages. The same word conveys different meanings in different contexts. This includes both polysemy, where words have related meanings, such as English glass, and homonymy, where they have different unrelated meanings, such as English bat. But we really don't know whether children hear multiple meanings for words, whether they use multiple meanings themselves, or what this means for language. Is ambiguity widespread in speech to children, as it is in adult-directed speech? Or might caregivers avoid using ambiguous words when speaking to children, similar to how they employ simpler words in child-directed speech? Do children show a restricted range of senses with respect to adults? This is implied by a heuristic, embraced by various scholars, that children have a single word, single meaning learning bias. And are words that are used with a more diverse set of meanings learned earlier or later than those with a single meaning? We really don't have the data, that is meaning-tagged naturalistic corpora, necessary to answer these questions. So we decided to collect a new dataset. Our general approach will be to tag word meanings for individual uses of words in longitudinal developmental corpora. Specifically, we chose words from the Communicative Development Inventory, identify these words in longitudinal childless corpora, and then have annotators select meanings from an appropriate ontology. Here we use WordNet 3.0 senses. These senses are enumerated, discretized meanings, kind of like multiple dictionary definitions. Then we can analyze the relative frequencies of the different meanings. To make this more concrete, I want to show an example of the tagging interface. So on the left is a transcript from childless. Words needing sense tags are in red, completed words are in green, and the currently selected word is in blue. On the right-hand side is the set of sense definitions and examples from WordNet, which are retrieved using the part of speech and the lemma of the selected word, in this case bus. Participants choose as many of the senses as they want. They can also choose I don't know or other meanings. This web app is built on top of ChildlessDB. So not only does ChildlessDB make analyses of child language corpora easier, but it's also quite convenient to build web apps on top of it. We want to tag longitudinal corpora that have a balance of dense sampling, cover a broad time range, and contain multiple children. So we choose the Manchester and Providence corpora, which contain 12 and 6 kids respectively. Note that our taggers used audio recordings only. While videos are available for most transcripts in Providence, they aren't for Manchester. Each of these corpora contain many millions of word tokens, so as I said, we're going to limit the analyses to specific ones. Here we limit to those appearing in the Communicative Development Inventory Words and Sentences instrument. Also, because our goal is to characterize as many words as possible, we don't need to tag all instances of high-frequency words and can instead subsample. Consequently, if there are more than 50 tokens per speaker role in a 3-month time period in a corpus, we tag just 50 of those tokens. Also, for now, we're just going to generally get one tag for each token. To give you an idea of how these filters change what needs to be tagged, I'll plot the total number of tokens with dotted lines, the much smaller number of tokens on the CDI with dashed lines, and the even smaller number of subsampled CDI tokens with solid lines. And I'll stratify that by caregivers versus children, red versus green. So you can see here that these two filtering steps drastically reduce the number of words needing tags. But even then, to get broad coverage across words, we still have up to 15,000 tokens in each 3-month time period. If each of these tags takes a minute of tagging time, we're looking at something on the order of 5,000 hours of tagging. With those numbers in mind, it's unsurprising that we aren't done yet. The results I'll show today are based on about 2,700 hours of annotation time, corresponding to the blue bars here. Since January, we've made more progress on Providence in green, but we still have a lot to do for both corpora in red. How have we managed to tag so much? Well, we have a heterogeneous mixture of taggers, in-lab research assistants, class participants, and subject pool participants across 3 universities. All participants code one of a small number of transcript selected from each corpus, as well as a random sample of double-coded tokens, so we can compute inter-annotator agreement and check how reliability varies across these different types of taggers. Evaluating agreement is a little complicated because it's a multi-annotator and multi-class coding problem. This plot of pairwise annotator agreement shows that in-lab annotators show higher agreement than class and subject pool participants, but are all above random baselines. I'll refer you to the paper for more details on how we evaluated and filtered participants. The analyses I'm going to show all focus on measuring the diversity of meanings, that is word senses, used in a sample. So before I get into analyses, I want to talk about how we measure this diversity. What we'd really like is a single measure of the diversity of sense usage, an index that increases if a speaker uses more senses, and also if the usage is more spread out across senses rather than focused on just a few. So here we use the measure of information entropy, which reflects the average predictability of each of the word senses for a given word type. To give some intuitions about how different sense distributions would cash out in different entropy values, I'll plot entropy as a function of the combination of three probabilities, corresponding to three different senses, which must sum to 1. To work through some examples, the point A on this space corresponds to a probability of 0.5 of sense 1 and 0.5 of sense 2, which is the same as the flip of a fair coin, or 1 bit of entropy. Point B is the most diverse usage, in that it entails equal usage of the three senses, with an entropy of about 1.58 bits. We don't actually see this ever in natural language. Point C is zero entropy. There's no uncertainty if sense 1 is always chosen. And point D is a combination of a probability of 0.77 for sense 1, 0.09 for sense 2, and 0.14 for sense 3. Glass, for example, shows a similar pattern to this. And I include point D because it has the same entropy as point A, even though it reflects the usage of three senses as opposed to two. So sense entropy will serve as a concise measure of diversity, but how are we going to get these probabilities of usage? So the challenge with our entropy measure is that point estimates of sense probability may be very biased, especially for rare words. First, words follow a Zipfian distribution, so we'll have a lot of words that are only seen a handful of times. Second, we can have highly biased, potentially Zipfian distributions of senses within those rare words. So we need to estimate the probabilities of many rare senses. And this really quickly becomes a problem. If we only see a word type once in a sample, for example, then its entropy is necessarily 0. Now this means we don't want a point estimate, but instead want to treat our annotations, that is our tags, as observations generated by some latent variable, that is the true underlying distribution of meanings for a given word in the sample. What we really want is an estimate of entropy that is constrained proportional to the amount of data that we've observed for the word. Hence a Bayesian approach to the problem. We can think of each word type as a weighted die, where sides correspond to different meanings. Then we can have more or less sure beliefs about the die's weighting based on how many rolls we see. Under the Bayesian approach, we need to place a prior over the possible sense distributions for each word. This prior should be weak enough that the sense probability estimates are still driven by the data. But we also want this prior to be asymmetrical, to capture the fact that most senses will be seen very rarely. So we use a feature of the WordNet dataset. The most common senses in WordNet are most often the first listed one. In fact, 55% of adult uses come from the first listed sense, with a similar number for children. So we choose an asymmetric Dirichlet prior that captures this general tendency and split the remaining mass evenly among the remaining senses. We then estimate the sense distribution for each word with Gibbs sampling and compute entropy for each word directly on the samples from these posterior distributions. With that entropy estimation technique on the board, I want to talk about the specific analyses that we did. First, we compared meaning diversity, that is sense entropy, in a previously tagged sample of adult-to-adult language to sense entropy in child-available adult speech using our newly tagged dataset. Second, we compared the adult entropy of adults and children in our newly tagged dataset. And third, we tested whether sense entropy in child-available adult language predicts the age children start to use a given word type, as measured by caregiver report. So I will start with a comparison of sense entropy in adult-to-adult language versus sense entropy in child-available speech. In this plot, each point will be a word type, for example, bus. Its position on the x-axis indicates the mean estimate of that word's sense entropy in our newly annotated childless dataset. On the y-axis, the mean estimate of the word's sense entropy under adult-to-adult language use, that is in the SEMCORE dataset, and I'll facet it by part of speech. I'll plot a diagonal which indicates identity, so points above these lines are ones that are more diverse in adult-to-adult language. As a statistical test for each word, we can look at the difference between entropy estimates from the MCMC chains. And specifically, we can check whether 95% of the difference between the two distributions is above or below 0. Red means non-significant, green means adult-directed is significantly higher sense entropy, and blue means child-available is significantly higher sense entropy. So when I actually plot this, we can see that words have comparable, if not higher, sense diversity in child-available speech compared to a sample of adult-directed language. We see diversity is largely symmetrical for nouns and verbs, while adjectives and adverbs show more diversity in child-directed speech. So this is inconsistent with the idea that caregivers use fewer word meanings per word type in speech directed at young children, at least for English learners between 18 months and 5 years. Next, we move to comparing sense diversity among adults, as you saw on the last slide, with children, measuring both using our new dataset. Again, we're going to use the same technique to estimate sense diversity and to test whether the difference is significant for each word. This analysis reveals comparable usage of nouns and adjectives, but adult caregivers show more diverse sense usage of verbs and adverbs. So it seems like kids are focusing on just a few senses of verbs and adverbs compared with their parents. Another analysis we can do here is directly compare the entropy estimates between different parts of speech. With respect to this plot, we can think of this as taking the marginal density plots and comparing them across the panels. This yields distributions for each part of speech that look very similar between adults and caregivers. But we see a clear pattern across parts of speech. Nouns and adjectives in general have the lowest sense diversity, followed by adverbs, with verbs showing much more diverse sense usage than other parts of speech. And just for comparison, I'll remind you that equal usage of two senses equals 1 bit of entropy. So one of the questions I raised at the beginning of this talk is whether children produce words with more diverse meanings later. This dovetails with an extensive literature which seeks to characterize which words are learned earlier or later by children. That is, relating children's early vocabulary to statistical properties of the input, as well as lexical properties like the number of phonemes. So what we can do here is take sense entropy for words where we have sufficiently constrained estimates and predict vocabulary knowledge as reported by caregivers on the Communicative Development Inventory, or CDI. Following Brzezinski et al., we fit a mixed effect logistic regression. For random effects, we estimate age by item random slopes. Then we take the same set of fixed effects as that work, the frequency in speech to children, the number of phonemes, how concrete the word is rated to be, how often the word appears as the only word in an utterance, the mean length of utterance that a word appears in, the strength of its association with child-directed language, and ratings of its valence and arousal. To these predictors, we add sense entropy, and we residualize frequency and concreteness with respect to the number of senses. The idea being that the number of meanings is what's driving frequency of use as well as perceived concreteness. I'll plot the coefficient estimates here for main effects as well as interactions with age. Filled circles will be significant. This reproduces the pattern of results found in Brzezinski et al., with one addition, which is we see a statistically significant negative main effect of sense entropy. Words with more diverse sense usage are produced later. This is consistent with work such as Roy et al. 2015, which finds that more constrained contexts of usage are associated with earlier production. So today I've presented on our efforts to understand the nature of the word meanings used in speech to children, as well as children's own productions. I described our annotation effort to produce a large dataset of the word meanings used in longitudinal child language corpora, appropriate for testing hypotheses about the nature of lexical ambiguity in early language. This annotation effort uses WordNet senses, subword definitions that provide broad coverage across words. Our first analyses of this new data set, which focus on the diversity of sense usage as measured by sense entropy, revealed that adults use comparable meaning diversity in speech to children as in adult-to-adult speech. Children are using multiple meanings in their own speech, primarily nouns and adjectives. And finally, words with more diverse meanings are learned later. To give you a sense of what we are working on next, we will be characterizing developmental change in more detail, testing whether sense entropy predicts adult lexical decision, and extending these sense tags using recent neural models. We hope these analyses and the dataset itself, which we will release soon, will enable new research into word meanings above and beyond word forms in early language acquisition. And with that, I want to thank my collaborators, as well as Dee Dong, who helped implement a lot of this, Mika Brzezinski, who helped us with the CDI modeling. Further, I want to thank our many annotators, the families in the Providence and Manchester corpora, as well as the original transcribers, and to our funding agencies. And finally, thank you for listening.